Hi there folks, my name's Cameron and today I'm going to speak to you guys about Faraday's law. So imagine we can take all that we know about electromagnetism and compact it down into just 4 short equations. Well, that's what James Clerk Maxwell did in the 19th century. He was able to show that these 4 equations told us everything that we know about electromagnetism. But one of them, it's called Faraday's law, named after Michael Faraday himself. He demonstrated that electric and magnetic fields are closely linked and they can actually induce one another. Let's take a closer look at the equation in its integral form. It shows us here that a change in magnetic flux through a surface will create a circulating electric field. But what is magnetic flux? So let's picture a bar magnet with its magnetic field lines. If we put an open surface near the magnet, the flux is going to be the total amount of field lines flowing through the surface. And if we move this magnet closer, then you'll see that more field lines are going to go through the surface, increasing the flux. But, according to Faraday's law, a change in magnetic flux induces a circulating electric field. So if we replace the open surface with a coil of wire, we would get an induced current flow. This is what is known as electromagnetic induction. However, it is worth noting that Faraday says it's a change in magnetic flux, and a stationary magnet with a constant magnetic field will produce no electric field at all. And here's some footage from the archives, which will show all of this in action.
This might look like a regular, uninspiring laboratory. But inside, as we shall see, is something quite extraordinary. Here we have found a peaceful coil of wire, preparing itself for the harsh winter ahead. At this time of year, the coil has become docile while it conserves energy. So we should be able to test Faraday's law without disturbing the coil. And we can do so with this magnet. We can connect our ammeter to the coil while the coil remains relatively immobile. Now we can see, as we insert our magnet into the coil, a change of magnetic flux induces a current. The current then returns to zero while the magnet is stationary. As we pull out of the coil, the change in magnetic flux is in the opposite direction, so we get a negative current, which then returns to zero while the magnet is outside the coil. So there we have it. By changing the magnetic flux inside a coil of wire, we can create a current in the wire just as Faraday proved. And now, I think we should leave the coil to rest.
Okay, and a big thanks to our guys there at the archives for digging that one out for us. Faraday's law still has its uses today, one of which is in generators, converting mechanical energy into electricity which can be delivered to our houses. If it weren't for Faraday, electricity wouldn't be so widely available. And that's all for this video. I hope you've taken some knowledge away with you, and thank you for watching.